All right, let's get started. We are near the end here. All right, two more lectures. Two more lectures, including this one. We have this lecture, we have Monday, and then we have Wednesday off, Friday's exam review day. So, what? What's that? I told you all that. I said that if you looked at the syllabus that I had that as a makeup day, and since we haven't had any snow days, I was going to hold myself to that. Well, there is that. I know. So if there's a blizzard, all right, let's see, 1, 2, 3, 4, 5, 6, 7. I wouldn't be surprised with the weather we've had.
I've gotten used to it being warm. Now I'm going to walk outside.
Okay, so let's be clear on the agenda. So you all are turning in homework 8. I have given you homework 9. It is due next Friday, yes.
So we have one more homework in here and one more homework in steel? Not
This is steel.
concrete.
In concrete, yes.
Are they both due Friday?
Yes.
Okay, so
That's why I was saying don't put the concrete homework off to the last minute because of this one.
yeah. Well, I mean, we got other homework to do next week.
Now, look. Every day. Every day.
At some point in time, it's not your phone, it's just us. You do all you can.
Your words, not mine. Okay. All right, everybody, settle down. A couple things. Number one, I've had so far a pretty low turnout on course evals. I really would like to get everybody to do theirs. Again, free points, so you just need to do it. I've only got, I think, like 5 responses or so. So please, the feedback helps. If there's something that you think should be improved for next year, please let me know. Again, we have our exam scheduled for May the 5th. I know some of you wanted to move it earlier, but I'm not doing that unless everybody's here, and everybody's not here. In all honesty, as a piece of advice, especially for those of you that are also in concrete, I think it's probably a good idea that the exam's on Friday, because one of the things that I know the steel and concrete folks have been saying is that the classes bleed together. So having one on Monday and one on Friday, maybe that separates that a little bit, So that's just my outsider's perspective, okay? Everybody okay with that? But again, we'll have that discussion, but I got to have everybody here, okay? So, and we're still missing folks, so we'll worry about that later. In the meantime, I want to get into our final topic of the semester, which is designing discretely braced beams, okay? Now, just a heads up, I did re-record the lecture from last time. It was a mess. We didn't have the examples worked out, so I went and re-recorded it. What's that? Well, thank you.
You're just a great guy, Really cares about his students.
Well, thank you. Okay, one thing I'll point out, so on this example, I wrote out the answers, the 1.67, the 2.05, and the 2.33. I also went and did example 23. As you can see, I've got that done in the notebook. The main reason for doing that is that during exam review, if you all have questions about it, I can pull it up. So that way we have that. But before we get into before we get into discretely braced beam design, I really want to make sure that discretely braced beam analysis made sense. Did anybody have any questions on discretely braced analysis? Yes? Okay. That's a good question. And that's really important for our discussion today. Bless you. The zones depend upon where your unbraced length is. Okay? So your zones are divvied up based on the 2 anchor points, L sub P and L sub R. Okay? So for case 1, in that example that we did, we had an L sub B of 5 feet, right? Okay, that was less than LP, right? So that put us in zone 1, okay? And for case 2, we were between LP and LR, so that put us in zone 2. And with me so far? All right. Anything else? That's the difference, yes. That's the difference. Any other questions? This is good stuff. Okay. In order to design a discretely braced beam, you need to understand that, what's on the screen, okay? You need to understand the LTB curve, the idea that there's 3 regions split up between LP and LR. You have zone 1 that's fully plastic. You have zone 2 that's inelastic buckling, zone 3 that's elastic buckling. You also need to understand that C sub B can serve to amplify your capacity. However, I don't care what C sub B does to your capacity, you're cut off at MP. All right? Everybody okay with that? Now, here's the problem with beam design. When we did columns, remember our column curve and it sort of went down and went like that? Remember we had an inelastic curve and an elastic curve? Barring material properties, put those off to the side, to draw the column curve, you only needed one property, and that was slenderness. You all had a homework problem on that, right? I gave you all a steel and said just plot the curve, and that was it. And that column curve was the same curve for every single column, the W10 by 49 and the W14 by 800, and everywhere in between, right? Okay. The problem with beams is that's not the case. The beam curve is a function of a lot of different parameters. For instance, if I just look at LR, I've got the section modulus, I've got J, I've got the flange centroid, I've got the radius of gyration, the B sub F factor, I've got LP, which is a function of the radius of gyration about the y-axis. There's a lot of different stuff that goes into the LTB curve. Unfortunately for beams, there is not one single LTB curve that works for all of them. If I wanted to plot the LTB curve for one beam and then look at another beam, I'd have to plot an entirely different curve. Each curve is unique. They're all shaped like that, but all the individual values are different. I mean, let's just take the L sub P and the L sub R's. If I go right here, every single shape has a different LP and a different LR, right? That right off the bat dictates that every curve looks different, okay? Does that make sense? So let me show, does anybody have any questions about that? That every curve is going to be different, unlike with columns where it was the same curve for every column. Everybody okay with that? All right, let me put this in full screen. Well, if you understand that, then I'm about to show you a little bit of a mess and then simplify it a whole lot. Okay, so let's see. We ended last time essentially summarizing our LTB expressions, zone 1, zone 2, and zone 3 as follows. And these expressions are essentially plotting the curve. Okay, and we did an analysis example. To design a beam, it's difficult because each curve is unique. So what the spec gives us is this. Okay, now this is a tab-worthy guide. If you have your tabs with you, you definitely want to do this. I want everybody to turn to page 3-99, and there's probably 20 or 30 pages of this guide. Now, I know, like, when you start turning through these pages, it starts to look like a damn mess. Like, I mean, like, start turning through them and kind of seeing. You'll probably start to get to curves that look like this, and you'll just go, you have got to be kidding me. Really? Now, this looks like a mess, but really, all that is every single LTB curve for every single section, all plotted on top of one another. Okay? That's what that is. What's that? There's no other way to select a section. That's the thing. Because each LTB curve is unique, there's no other way to go about it. However, the folks who wrote the manual, they were a little bit clever about some things. Let me show you something. Have you noticed, thumbing through those shapes, I mean, start thumbing through them, you'll see that some of the lines are dashed and some aren't. Y'all see that? What do you think those solid lines represent? No, it's not different zones. What's that? Just like the bold ones in the ZX tables. Remember that? Remember how they're in the ZX tables they were grouped, but then that top row was bolded? Why was that top row bolded? It was the lightest within a given group, right? If you look, what you'll see is those solid lines are the lightest within a given chunk. So for instance, I'm looking at this page and you can see there's a lot of stuff going on here, but I'll sort of show you how this works. Okay, now if you notice, I want everybody to look at the top left corner of the pages. What's FY? 50 KSI. So obviously, if you have a different grade of steel, you'd have to use a different guide. Well, what's C sub B? 1. Every single one of these figures, every single one of these plots were plotted contingent upon the fact that C sub B equals 1. So here's what you do. When we're in design mode, we're rarely dealing with the beam where C sub B equals 1. Usually C sub B does not equal 1. It's usually larger. So what we do is we enter the table. On the x-axis, we find our L sub B, our unbraced length. And on the y-axis, we find our moment. But our moment is not the factored moment. It's the factored moment divided by C sub B. We divide that C sub B out so that we're sort of dealing with a moment where C sub B equals 1. And the way that works is this. Okay, so we enter that chart with those two values. So let's say we've got an MU over CB of, let's say, something like 272.5, and we have an unbraced length of 20 feet. So this is what I did. I say, all right, let's find 20 foot on the x-axis. Let's find that value on the y-axis. Notice we're using the blue axis, not the green one, right? So find that, and that point's about right here. Okay, everybody okay with that? Now I propose that everything up here in this upper right region would be a safe section, okay? Because everything in the upper right, I mean, what is that indicating? Anything in the upper right would be a section that has a larger moment capacity and a larger unbraced length. Those are all conservative scenarios. So anything in that upper right portion is fine. Which section do I pick? Do I pick the W21 by 68? I say no. I say you pick the W14 by 61 because that's the solid line. That is the lightest section within that given group, okay? Now, just so you know, the solid lines in this chart and the bold lines in the ZX tables may not necessarily match. But again, we're talking about different scenarios. We're talking about buckling as opposed to yielding, so it's a different scenario. Make sense? Everybody okay with that? Okay. Now, once we select a section, we have to go back and check it. There is no, I don't feel like, no, you have to check it. And here's the reason why. C sub B can serve to falsely give you a beam design. In other words, how can I put this? You know, what does C sub B do? It amplifies your capacity, right? It makes it larger. But it cannot be larger than M sub P. Because of that, it's very possible in design that you can get, I guess what I like to call I guess the best way to call it, like almost like a false positive, that you can select a section, it looks like it's good, but then when you go back and do the math, you find, no, it's invalid, okay? And that'll make sense when we start getting into and digging into an example, okay? Everybody with me so far? Okay, all right. Then let's take a look at this example. This example is a little involved, but and we're going to do the example 4 times, okay? Because I want you to really understand beam design. And the only way I think that you can really understand it is to go through different scenarios. So let's really try to digest what's going on here. Okay, so I want to select the lightest section. It's going to support a uniformly distributed service dead load of 600 pounds per foot. Now that includes the beam self-weight, so we're never going to have to go back and update dead loads with this problem. You would if you were going and, let me put it like this. if that statement wasn't there, with every beam that we pick, we'd have to go back and check to ensure that our estimate is fine. But for the purposes of this problem, we'll just say that 600 pounds per foot includes the self-weight. Now this beam also has a concentrated live load moment, or live load of 40 kips at midspan, okay? So unfortunately with this problem, we have a substantial dead load and a substantial live load, so we're going to have to go through and compute C sub B. So this will give us a little practice on that. And this is really valuable practice for your homework and for the final celebration. So it's definitely something you're going to want to pay attention to. Now the beam is 20 foot long and it's simply supported. In addition to all the flexural requirements, ensure that the beams have adequate stiffness to resist the live load deflection of L over 300. Everybody understand the beam design, what we're after? Everybody okay with this? Now, the beam is 20 foot long. What is its unbrace length? Well, I didn't say that, okay? Let's look at the next slide. We're going to design this example 4 times, okay? We're going to design it looking at 4 different cases. Now let's look at case 1. Case 1, we're going to take C sub B equals 1, and we're going to take LB equals 20. That is the worst case scenario, okay? Does that make sense? Longest unbraced length, and we're not accounting for moment gradient, okay? From case 1 to case 2, we're going to say, you know what, let's actually go through and compute that C sub B value, and let's see how that affects the design. And you will see that it does affect the design. Case 3, we're going to put a brace at midspan, right there at that point load. So that means L sub B is 10, okay? We're still going to take C sub B equals 1 on case 3, and then case 4, we're going to go through and compute it. Everybody okay with this? Okay. The idea is I want you all to have a lot of practice with this table, and I want you to understand how L sub B and C sub B affects your design. Everybody okay with this? And effectively, I would say this is about our last example for the semester. I'll show you all shear at the end, but it's not a big deal. Excuse me. Save the best for last. Okay. Okay, example 24. Okay, so let's look at the beam real quick, beam parameters. What's going on? Okay, what was our dead load? It was, that's a fair way of putting it. And then, now, what would this be? $1.2 times that, so what is that? If I just went ahead and, it's 6 and then 12, so 0.72. 12 times 6, 72. Did I do that right? All right, now we've got a live load of 40 kips. So what is our factored live load? There we go. 64 what? There we go. Now, on the homework or on the exams, this becomes a trend. If I see you all trying to take that point load and turn it into a distributed load, no, don't do that.
Ow.
Make sure to yell for the recording, right? Is that what it was? You can't do that because you're going to get a different moment and a different deflection, okay? Everybody okay with this? It's just, we really need to make sure we're clear on that. Now, before we go into moment requirements, I want to take a little bit and I want to discuss serviceability requirements. Okay? Now, I guess I should also put the span length is 20 foot, which is 240 inches. Okay. Now, let's talk about serviceability. Okay. Now, what is the maximum deflection allowed? Maximum live load deflection, I guess I should say. Say it again. L over 300. And what is the actual live load deflection? Ooh, that means you got to go through your manual, go through the guides. Oh no. By now, you shouldn't be complaining about having to turn to different pages in your manual. We're on lecture, what, 34? It's a little late. What? Oh.
Then I'm gonna complain about dying.
Afterwards, that'd be a feat.
Surprise. I can do anything I put my mind to.
Say it again.
PL cubed over 48 DI.
Is everybody able to find that? I mean, by now, that's a pretty common one. Hopefully, you kind of remember that one. So. Oh. Now, what case was that? So, all we really have to do is, I mean, to keep this simple, we can just set these two equal to one another and solve for I if we want to keep this simple. I mean, yeah, technically it's an inequality, but I think we recognize that Ix is going to have to be bigger than whatever we solve for. So the live load, set that equal to the maximum. So and solve, and I propose you're going to get an Ix minimum of PL squared over 48E. Y'all see how I'm doing that? Flip and multiply that over, L's cancel. So, everybody okay with that? So 300 times, what's the load? It's 40. What do you not do with deflections?
Oh. Whoops.
Well, there goes the homework.
Oh no, my mind's made up. I didn't record that. I don't put the exam solutions on YouTube. 2 plus 2, in fact, equals 5, right? All right, what do we got for this? $496.55. These are actually, so we'll just keep it simple and say 497. These are actually pretty modest requests for a beam for a moment of inertia. I mean, what were we getting on the homework if you didn't factor the loads? What was it, like 5,900, 5,800, something like that? That's an algebra thing. I mean, what did I said that one problem's going to have a lot of algebra. And no, it's not. No, it's not. You're using a heavier section. That's not saving money. Camera for dead load. All right. we're going to take this one case at a time, okay? So case one is really meant for us to appropriately understand how to navigate the beam charts, okay? So case one, what was the deal with case one? I've never heard it referred to that. Okay. All right, so I want everybody to make sure they're clear on what's going on with the analysis. What's the distributed load? Now this is a moment calc, not a deflection calc. There we go. And this, 64. Now that's 10 feet and that's 10 feet. Now in terms of bracing, we only have bracing here and here, right? Okay. Because the beam is 20 foot long. It just so happens that its length and its unbraced length are the same. That's not always the case, but it just so happens to be in this scenario. Now, if this is our beam, how do we compute MU? Take it one load at a time. Distributed load. WL squared over 8. What about the point load? You're guessing. Look, you're at. Yes. 497. I think that's what it was. Yeah. Is that what it was? There we go. All right. Settle down. I need an answer on this one. $356. Do I have a second on that? All right. All right, does everybody have this? That's right. Oh. All right, I'll give you 20 seconds. Actually. No, I'm not. Yes? I like to say foot kips because it reminds me of foot pounds, you know, like torque. But 2 times 3 equals 3 times 2. So I'm a foot kip guy. That's just me. I don't like that.
Is that actually what it's called?
No, I call it foot pounds.
Yeah, but you call it foot kips.
I disagree. Okay, all right. Are we good? Now, come on. All right. I'm gonna move on a little bit. All right, everybody, settle down. Goodness gracious. All right. Goodness. I know it's near the end, but we don't get through this, your homework's gonna be real fun. All right. Now, what C sub B is 1, right? So MU over CB is 356 foot kips. Now this is what I want you to do. I want you to go into the beam charts, and this is where it takes a little bit of practice, and everybody's going to have to do this together. Go into the beam charts, and we're going to go into the beam charts with these values, with LB is 20 feet and an MU over CB of 356, okay? So 356 foot kits. Now what I want you to do is I want you to find this point and then tell me what is the most economical section. Excuse me.
So do we read the one dashed closest to the point?
Now what did I say? The solid one.
Okay, W16 by 67. But I don't know if that's right.
Well, let's use the golden rule of the second. Is there a second on that term?
Yeah. Sometimes I guess sometimes the lines cross and then like one becomes from solid to dash.
You're right, because once you get past that region, one section becomes more economical. Everybody got the 16 by 67? What page are we on?
125.
125. All right. Do you find it? Mr. Lewis? Mr. Hampton? Mr. Chadwick? Mr. Schaffer and Mr. Dowdy? Mr. Crookshanks? The 67? Mr. Adkins? Mr. Fadiga? Okay, where are we at? All right, so, yes. Okay, I didn't hear a single thing you said. What? What? Because you have different load factors with ASD versus LRFD.
Because then it wouldn't be the same for
Let's go
ASD.
up by 5 every line.
For ASD, it's about 10.
Oh no, it
The,
Gives up by 3.
the reason, hold on. The reason why is because you're not factoring loads in ASD and you're using a different safety factor. And if you go through and do the math, the ratio is 2 to 3. So. Yeah. All right, is everybody able to find this? You two? Okay, everybody good? Now, everybody listen to this. I propose you do not need to go back and check this section for one very simple reason. What was C sub B? 1. Okay. So I propose that the answer is because what was the chart drawn off of?
1, okay.
It's incorporated, yeah, and the self-weight's incorporated. Now, case 2, this is where we really got to pay attention, all right? LB is 20 feet, but C sub B does not equal 1. In other words, we have to compute it. So what's our formula for, you have a question?
Yeah. In that case, does it mean we can't?
We are not able to use these tables anymore. These are all C sub B is equal to 1.
That's where I said we have to go back and check it. We're getting there. Bear with me. All right. C sub B does not equal 1, which means we have to compute it. Now, let's go back. How do we compute C sub B? The 12.5 M max divided by 2.5 M max, etc., right? Now, I want everybody to look at this image up here, okay? Now, I'm going to put a coordinate system on here so that we can all speak with the same, reference. Okay, so I'm looking up here at this beam on the top, and I've got an X and Y axis, okay? So what do we have to determine? We have to determine MA, MB, MC, and MMax. Everybody with me? Now the beam is braced at the ends only. Okay. So at what x coordinate will MA occur? Who said 5? 5. It's exactly right. Where will MB occur? At what? X equals 10, right? MC at x equals 15. Everybody with me on that? Okay. Now, let's use a little bit of common sense on some things. The beam is symmetrical and the loading is symmetrical. Where is Mmax going to occur? At midspan, right? So would you agree that MB and Mmax are going to be the same value? What value is MB and Mmax? 356, right? Because the WL squared over 8 and the PL over 4, that was taken at midspan. Everybody okay with that? So, first off, MB equals Mmax equals 356 foot kips. Is everybody okay with that? Now, how am I going to determine, well, okay, let me not skip ahead. MB and Mmax are equal. Everybody okay with that? Would you agree that MA and MC are going to be equal? They're going to be the same, right? How do I determine the moment right here? Well, we could solve for reactions, cut sections, some moments, or we could go to the spec. Go to table 323, everyone. Go to your shear and moment guide. Now, is everybody able to find this? I'll call it M sub W. Is everybody able to find that? See what I'm talking about? Well, that's for the distributed load. Tell me what is the function going to be? Yeah, for the point load. Say it again. Px over 2. Now you got that as case 1. This was case 7. Is that right? Case 7? Okay, so watch this. I propose, now keep in mind you're using factored loads here. I propose that MA equals MC equals the following. So watch this. 0.72 kips per foot times 5 feet over 2 times 20 feet minus 5 feet plus 64 kips 5 feet over 2. What does that equal? Now, well, hold on. Let me, before we start doing calcs, does that make sense? See how I'm just plugging in x equals 5 feet? Now let me ask you this. Could I plug in x equals 15 feet? Well, I would argue on the first equation, yeah, but not on the second equation. There you go. Exactly right. Okay? Does that make sense? Anybody have any questions on that? Does anybody have a moment for me? 187. Do I have a second on that? Yep. So, if C sub B equals the following,
How much harder would it be if we didn't do the CCP stuff and like calculated exactly? Just like that, right?
oh, very. Very. Prohibitively so. you'd had to break out numerical solution techniques and... Oh, yes, you have. You all have done numerical differentiation and integration and all that. Oh, that's what it's called. All right, what do we have for a C sub B? Instead of plugging the values in, these two are 187, these two and that one are 356. Can somebody just plug them in? 1.295? Do I have a second on that? You second that. Good. Everybody okay with this? Now, Mr. Cruikshanks, you made a point that we're not going to be able to use the guide. Okay. What I would say is we're not going to be able to use the guide directly. Okay. Directly. Let me explain. We'll be able to use it to pick a trial section, but we will have to go back and check it. All right. This is what I'm going to do. All right, so help me out. What is MU over CB going to be? Now, when we do MU over CB, we're looking for the maximum moment within a segment, in which for this, it's MU for the whole thing. So, MU over CB. 274.9 foot kips. And what is LB going to be? Now, find a section. This will be a trial section. (14 by 61). Do I have a second on that? Now, let's say that this section works. What happened? All right, what happened from case 1 to case 2? It got lighter, and it got shallower. There's no reason not to use C sub B, no reason whatsoever. Does this make sense? As long as we can verify that works, which is what we will do on Monday. However, there is one thing I do want to do real quick. Bless you. Something I realized I forgot on case 1. Let me scroll back up here to case 1. What was our answer, a W16 by 67? What's the moment of inertia of a W16 by 67? I'll put that over here in red, so note. I just realized we completely forgot that. So what is IX? You could find it in table 1 or table 3-2. It really doesn't matter. 954. What is that? Why did I care about that? To make sure it meets deflection requirements. Exactly right. So this one was good. Okay. If it wasn't, we'd just have to use the IX tables to find a section. Does this make sense? Okay. Any questions on this? Any questions? Now to check this section, you really just do what we did in the last example. Just pull your beam factor, your LP, your LR. You've got the C sub B value, so you just analyze it and determine phi mn. If that's greater than or equal to mu, you're good. We'll do that on Monday, but yes. Oh. Anything else? Did I not? I thought I passed. Did I pass the sign and shake around?
Yeah.
For sure.
Oh.
Sorry.
See, now, if you were here at 9 o'clock.
You weren't here at 9 o'clock.
Actually, I was here earlier. That wasn't
Yeah,
working.
and then you left, so it, but no.
I left to get the solutions for homework 8.
I legit do have.
Okay, real quick. For concrete. Goodness gracious.
So why couldn't we just use the IX tables to begin with? Because just comparing to get something that has minimum IX, it would be a W18 by 35, which is.
Pull the fee in. Now, hold on. This is really important. Everybody, okay. Your question, and then we'll leave. Your question was, why don't we just use the IX tables to select a section directly? Okay. Now, you use the IX tables, and you got what section? W18 by 35. Somebody go to the ZX table. Yes, you do. All right. Now tell me what is phi MP for that section?
249.
Wouldn't work anyways. That's a great question. Her design philosophy that she brought up was, why don't you just select by IX? That is actually a completely valid philosophy as long as you go back and check the capacity. Now what we found when you check that section is that the phi MP is or phi MP is what? 249. So regardless of what math we do, capacity can't get above MP, which is too low. But let me be clear. What she's bringing up is a completely valid design philosophy as long as you go back and check it. Well, you could use the ZX tables, but you're going to be iterating like crazy because if you just use the ZX tables directly, you're making the blanket assumption that LB equals 0. Not saying it won't work. You're going to iterate like crazy. Is everybody good? All right. Did everybody get a copy of the homework? All right. Due next Friday.